It looks good.
Yeah,
Okay,
very good,
okay,
Sensei.
okay, good.
Kasahara.
Yes.
Okay. Okay, Kasahara Sensei. So it's already 1 p.m. in Indonesian time here. I think we can start for the session.
Yes.
Okay, thank you very much. Mr. Praitno Abadi, can you hear my voice? Mr. Praitno?
Yep.
Okay, thank you. Okay, let's we start the session today. Okay, thank you very much, everybody. Good.
Dimas Aji.
Hadir,
Okay.
Bang. Hadir.
Okay, can you hear my? Okay, so in order to
Linknya di
save
mana
the
ya, Bang?
time, on behalf of Telkom University, we will start today's session, Sensei. Sorry, ini Dimas Aji.
Oh. Maru-san. Maru-san, can you hear me? I think the condition is not good. Maru-san, can you hear me? Okay. And can I start?
Kasahara Sensei.
Yes.
Yeah, okay. Let me introduce myself. So Umar-san asked me to chair this lecture. So yeah, let me introduce myself. My name is Prayitno Abadi. So I'm also graduated from Nagoya University from Japan. So I'm working with Shiokawa Sensei and Otsuka Sensei. So
Yes.
yeah, but during my study there, I'm not in ERG project, but I am in a P-STEP project.
Yes.
Okay, but I think Umar-san has connection difficulties because he is now in outside campus. So I think he has a business trip in Eastern Indonesia. So I think, yeah, you can start your lecture. So I think, yeah, you can start now.
Okay, thank you very much. Okay, so hello everyone. So my name is Yoshiya Kasahara from Canadian University in Japan. And so Dr. Umaru-san was studying the wave propagation observed by the Arase satellite, ERG satellite, and he graduated our laboratory and obtained his PhD. Okay, so today I will introduce our research. Okay, so the title of my lecture is Signal Processing Technology in Radio Science for Solar-Terrestrial Research. Okay, so can you see our slide? Okay.
Yes, we can see. We can see.
Okay, so I'll start. Okay, so I'm belonging to the Advanced Research Center for Space Science and Technology, Kanazawa University. Okay. Okay, so first of all, I'll briefly introduce the research background. Okay, so here we show the space environment around the Earth. Okay, so space environment around the Earth is shown as here. So our Earth, so we depend on the space systems such as communication satellites, broadcast satellites, and meteorological satellites, and so on. But so you see here, this is a picture of the movie of the sun. And you see that some explosion is sometimes occurring on the surface of the sun. And so because of this kind of explosion, so many risks associated with the environment in space occurs, such as radiation hazards for astronauts and a single event upset of IC and the degradation of solar panels and so on. So we need to know what kind of cause will be affected to our human beings' life. So we need to know the weather in space. Okay, so I show the first the term space weather. Okay, so space weather is a concept of changing environmental conditions in our space. Okay, so we need to know the environment, current environment of the space, because it is very important to for the astronauts and also our human beings' life on the surface of the Earth. So the definition of the space weather is a condition in space that affect the Earth and in its technological systems. Okay, so actually, such kind of services are already provided. Okay, so this is one example. Okay, so here we show one example of the URL, and this is the space weather center provided in the US. Okay, so this is a weather forecast yesterday. Okay, so you see that the condition of the surface of the sun and also the condition of the space environment around the Earth. So you can access this site and you know the current environment of the space. Okay. Okay, so I'll briefly introduce the our spacecraft developed in Japan. Okay, so we show first the two spacecraft named Akebono and Geotel. Okay, so Akebono was launched when I was a university student, and Geotel is also launched 30 years ago. And these spacecraft were orbiting around the Earth to measure the environment of the space. And now we are measuring the space environment using the spacecraft named ERG and renamed as Arase after launch. This spacecraft was launched 2016, 5 years ago. And in parallel, we also developed many kinds of spacecraft for the planetary mission. The first one is Nozomi for the Mars exploration, and the Kaguya is a lunar orbiter to measure the environment around the Earth, around the Moon. And now we are operating the new spacecraft. The mission name is Bepi Colombo, and our name of the spacecraft is Mio. And this spacecraft was launched 2018. And this spacecraft is now approaching towards Mercury. But as you see that this spacecraft mission takes so long time for the development. So we develop such kind of spacecraft every 10 years. Okay, so by using this kind of spacecraft, we can measure so many radio waves occurring from the surface of the Earth and also coming from the Sun and also coming from Jupiter and so on. Okay, so this is one example we measured by Geotel and Akebono, and this is also the example of Akebono. Okay, so by the changing the environment around the Earth, so many kinds of natural waves were generated in space. For example, if some storm occurs in space, we can find such kind of very interesting shape of wave. This is called chorus wave. I will introduce in the introduction in Arase. And so you know that so on the surface of the Earth, we have so many lightning, and from this kind of lightning, another kind of waves are generated, and this wave will propagate in the space. So we can call it lightning whistlers. And so this is a kind of wave zoo measured by geotel satellites. So you may see so many kinds of wave. Maybe it is a little bit difficult because such kind of waves are physically meaningful, but I will skip today. And by measuring, so to measure this wave, we develop a wave receiver, and we mount this wave receiver on the spacecraft. Okay, so first of all, I will briefly introduce the propagation characteristics of radio wave. Okay, so you may know that radio waves consists of electric field oscillation and the magnetic field oscillations. And this is a kind of radio wave. And okay, so this is propagation direction. And so this kind of oscillation propagate toward this direction by oscillating, by combining with E field and B field. And so nominally, the propagation velocity is equal to light velocity in vacuum. But in space, we have so many kinds of charged particles called electrons and ions. And so because, so caused by the existence of this kind of charged particles. So we call this plasma. So the caused by these charged particles, radio waves interact with electrons and ions, and it causes the waves reflection and refraction and reduction and so on. So by measuring such kind of waves in space, we can know the environment in space. Okay, so this is schematic picture that, for example, some kinds of waves are generated caused by the space storm. Then this wave will propagate toward this direction, for example. Then we can measure this wave by the satellite. Okay, and so maybe you know that radio waves propagate straight, but if there are plasma, so electrons and ions exist around the Earth, then these waves will reflect like this. So they propagate not straight, but curving like this. So that if we measure this kind of radio wave, we can know why it was measured at this point. And so this is a kind of CT scanner, you know, that for the medical measurements. So the spacecraft is orbiting many times around the Earth. So by measuring the radio wave around the Earth, we can know the three-dimensional structure of the plasma density around the Earth. Okay, so this is one example. So we measured from the Akebono satellite. So Akebono was operated for more than 20 years, and we mounted so many kinds of instruments on board the Akebono. So for example, magnetic field, DC magnetic field, DC field, and ions and electron detector, and radio wave receiver, and so on. And we operated low frequency wave receiver on board Akebono for more than 20 years. And so as a result, we got so many amounts of data from Akebono. So the spacecraft is very old, so that we recorded all data on the magnetic tape. The total amounts of magnetic tape is more than 28,000 tapes. And but magnetic tape will be so old, so that to reproduce this data, we reproduce this data, and we converted this data into digital now. So total amount of the data becomes about 20 terabytes so far. Okay, so by using this kind of wave data, we can monitor the radio wave from the sun. So we can know the activity of the sun by monitoring the radio wave generated from the sun. And also we can monitor the radio environment around the Earth and the other planets. So we can know at where and when these waves are generated and propagated to the observation point. And this kind of measurements is a very important role, key point to know the environment of magnetic storm and lightning and aurora environment. And measuring these parameters, we can know the density of the electrons and ions and the temperature of the charged particles. So by using this information, we can know the current situation of the space. And so in the future, we can forecast the environment by using these data. Okay, so this is one example. So here we show the wave intensity, average intensity measured by the Akebono for 10 years. So this is the Earth, and this is equator, and North Pole and South Pole. So we show the intensity of electric field, average intensity of the E field at 1 kilohertz, 3 kilohertz, and 5 kilohertz, and 10 kilohertz. So you see that intense waves exist around this region like this. So we know that this kind of waves are concentrated around this region. Okay. So this is a movie of the intensity of the electric field measured by the Akebono. So you see that these kinds of waves are actively changing every day. So by measuring this kind of wave, we know how active the space environment is. Okay, so let's move on to the signal processing method operated on the spacecraft now. Okay, so we measure many kinds of data on board the spacecraft, and we send these data to the Earth. So, of course, we need as much data as possible, but, sorry. Okay, so this picture shows how we send the observation data to the ground. Okay, so by using this kind of long antenna, we measure the electric and magnetic wave field, and we receive these waves on board the spacecraft like this. So this is a wave receiver mounted in the spacecraft. So we measure this wave signal, and we process this data by using the onboard CPU. Because the total amount of data is so huge, and we can't send all the data to the ground. So we process this data by using this CPU, and we send the telemetry data to the ground after the editing the measurement data. And these data will be stored in the database. Okay. So, okay, so this schematic picture shows the function of the smartphone. Maybe you know you use in usual. And as you know that the smartphone can be installed so many kinds of applications, such as the application for map and navigation, and application for mail and SNS and so on. And you can enjoy music and movie by using smartphone. And you know that this is because you can install so many kinds of application software inside the application, inside the smartphone. And such kind of performance and function can be changed and upgraded by rewriting the applications. So in the same way, we can rewrite the onboard software. So we call our receiver as software receiver. And so by changing or updating the software, we can install so many kinds of functions on board the spacecraft. Okay, so basically we measure so many kinds of waveform measured on board the spacecraft. So this is a kind of waveform measured by the spacecraft. And so by measuring this kind of, so you may see so many strange shape of waveform by Kaguya, Akebono, and Geotel. So we show these data to the ground, but the total amount of data is so huge. So we need to manage these huge data on board by using the software. Okay, so you know that the unit of information is shown by a bit. So 1 bit represent or a 0 or 1, and 1 byte means 8 bit. Okay, so to convert the waveform measured on board the spacecraft, we convert these data into digital data. Okay, so originally the waveform is like this. So this is intensity, amplitude of the waveform. Okay, so to convert this analog waveform, we first sample this waveform like this. So we call this sampling. And then we digitize and quantize this amplitude like this. And finally, we convert into binary code. And then we send to the ground. Okay, so for example, you know that the music CD consists of so many digital data. So in nominal music CD, one sample consists of 16 bits. And sampling frequency, that means how frequently we sample the music. So nominally, music CD use the sampling frequency at 44.1 kilohertz. That means 44,100 samples per second. That means the total information content of the stereo music is becomes like this. So 16 bit and 44,100 samples, and 2 means the stereo. So right and left sound. So in total, the total amount of data becomes 176 kilobyte per second. That means if we measure or we record the music for 1 hour, the total amount of data becomes 635 megabytes per hour. Okay, so this is too huge for our case. Okay, and this is a case of the picture, for example. So if we capture the color photo, the color photo consists of red, green, and blue. So RGB data. So the color data consists of 3 components of colors, and each colors consists of grid of the like this. So by changing the intensity of at each point, then we can make a color photo. Okay, so for example, so color picture with 920 times 480 pixels, then total amount of data becomes like this. So 1 byte per pixel times 3 colors and number of pixels. Then it becomes about 1 megabyte. So in the case of movie, the movie consists of 3 30 pictures per second. That means if we make such kind of movie by using this color picture, it becomes 30 megabytes per second. So if we record this data movie on CD, we can only record 20 seconds. But you know that you use the more compressed data for the smartphone. So when we edit the measured data, we need to compress the data. Okay, so how can we compress the information? Okay, so using compression technique, we can store a lot of music or movies in one CD or DVD, and also send this data via internet or mobile phone, because we can compress this data. Okay, so for example, in the case of a spacecraft mission, so this is a case of Mercury orbiter mission. In nominal, we measure low waveform with a data rate of 5.2 megabit per second. But the average telemetry data rate is only 4 kilobps. So the measured low waveform is too huge to send back to the ground like this. So we develop a data compression technique on board for onboard software. Okay, so the one scheme for the data compression is installed on the spacecraft. So we need to develop intelligent data compression algorithm with very fast and also fast computation time and also high compression ratio. But it is impossible to compress all data into 4 kilobps. So we also implemented the data selection function on board. Okay, so I explained so how intelligent our wave receiver is. So by controlling the software, we implemented the spectral analyzer for high time and frequency resolutions, and also waveform receiver for very broadband and wide dynamic range waveform. So we implemented the data compression, several kinds of data compression technique on board. So one is lossless compression mode, and another one is lossy compression mode. And also we implemented the data selection technique on board like this. So it is very important to choose very important and meaningful data from the measured data. Okay, so this is one example we implemented on board Kaguya lunar orbiter. Okay, so maybe you don't know what the meaning is, but this is the original data measured by Kaguya. And so red part means the very intense wave were observed, and the blue one is no meaningful data. So by checking the intensity level, we mask this part, and we send only for this spectrum data. So that means we select the important data by checking the threshold level for the data. Okay, so this kind of onboard selection algorithm was implemented on board Kaguya spacecraft. Okay, so next, so I will briefly introduce what kind of data were obtained by our space mission. Okay, so this is one example. So this is a Kaguya case. So we launched our spacecraft in 2007, and we inserted our spacecraft around the moon like this, and we continued our measurement for 1.5 years like this, and we successfully obtained so many kinds of wave around the moon. And another mission is here. So this is called Bepi Colombo. This is a name of scientist who studied the Mercury. Okay, so the Bepi Colombo mission consists of two orbiters named MMO and MPO. And MMO is developed by JAXA, Japanese Space Agency, and MPO was developed by ESA, European Space Agency. And we combined two spacecraft on board the, I don't know the exact name, but the carrier to carry the two spacecraft to the Mercury. And this mission was, so these two spacecraft was launched 3 years ago. And so these spacecraft will reach at Mercury in late 2025. That means we need 7.5 years to approach to the Mercury. Okay, so so we call this spacecraft as MEO after launch, and so we are now waiting for the measurements because we don't do anything for the journey phase because this spacecraft mounted this kind of long antenna, but in the cruising phase, we don't extend this antenna. So that means we can't measure anything. But this instrument was developed by so many institutes, including Kanagawa University, Tohoku University, Japan, and Kyoto University, and so on. And also, we developed with the other European countries, such as Sweden, France, and Hungary. So this spacecraft was developed. So we started our mission around very early phase of 2001. So it means so the development was continued for more than 18 years. Okay, so this is another mission we call Arase. Okay, so this is a schematic picture around the Earth. So from this direction, the sun ejects so many energetic particles towards the Earth. But the Earth consists of very strong magnetic field, so that this becomes a kind of barrier like this. But inside around the Earth, so huge energetic particles were trapped around this region, and we call this radiation belt or Barnum belt here. So around this region, we have so many charged particles, energetic particles, and this region is very risky for the astronauts because the total energy of the charged particle is so huge. And this is a result from our Akebono results. So the radiation belt consists of two regions. One is inner belt, and another one is outer belt. And so this picture is 1 year data measured by Akebono. And from here to here is a distance from the surface of the Earth. So you see, red part is a very risky region. That means very energetic electrons are trapped inside of this region. So this is inner belt, and this is outer belt. So you see that this kind of energetic particle suddenly disappears and then appears again like this. So, for example, so here we don't see so many radiation charged particle here, but here we see very intense or very a lot of charged particle here. So this charged particle were generated by
Winterman lagi.
storm here.
Winterman tuh.
To know when and where the charged particles are generated. So we measure the environment inside of the radiation belt by using our spacecraft Arase. So to measure inside of this radiation belt, we developed one spacecraft named Arase. So the Arase is orbiting like this, so that the Arase measures inside of the environment of the radiation belt. But it is very difficult for the nominal spacecraft because the energetic particle hits on the spacecraft. Then some electric circuit will be destroyed. So we sealed it for the harm of the radiation to protect the Arase. So it become possible to measure inside of the radiation belt. Okay, so this is a picture of the Arase, and we launched this spacecraft in 2016 December. And our instrument is here, so PWE, plasma wave experiment. And our plasma wave experiment consists of sensors and receivers. So we call electric field sensor as WPT, wire probe antenna. And we measure the magnetic field wave field by using the triaxial magnetic search cords. And we implement 3 kinds of receiver inside the spacecraft for the lower frequency range and the middle frequency range and the higher frequency range. And so this is a picture of our satellite. And here we have the magnetic search cord, magnetic field sensor. And this is wire probe antenna. And after launch, we extend this wire antenna. And inside the spacecraft, we have a receiver named PWE Electronics. So inside of this receiver, we have 3 kinds of receiver like this. Okay, so this is one example of our data. So maybe it is very difficult for you what it is, but you see the shape of the wave phenomena is different like this. And if we magnify one of these data, so you see very structured spectrums are observed. So by measuring this kind of fine structured wave, we can know when the magnetic storm or space storm occurs. Okay, so here I will introduce one of them. So this is one example of such kind of very fine structured wave. And so here you see the frequency of the wave. So the frequency of the wave is 1 kilohertz up to 1.5 kilohertz. And this is time. So from here to here is about 10 seconds. And this frequency range is almost the same as music. That means you can hear if we convert the waveform into the sound. Oh, sorry, can you hear? No?
No, we cannot hear.
Okay, okay. I'll change, sorry. Okay, I'll try again. Can you hear?
Okay, still we cannot hear.
You cannot.
Yeah, I cannot. We cannot.
Oh, you cannot.
Yeah.
Oh. How you can? Sorry. This is a kind of very.
Does it work in your PC, in your laptop?
Yeah, on my laptop. But okay, still makes.
Okay, I don't know. I cannot hear. So everyone here can hear the. Okay, I think this share screen the Zoom is cannot share your sound. I think the host must adjust the share sound in the Zoom. Sensei. Hostnya siapa, Mbak? Hostnya di sini siapa? Host Zoom-nya?
Ini di Pak Yosianya bisa deh Pak. Jadi tinggal share
gitu.
screen, terus di situ ada tombol.
Oh iya.
Share screen dulu terus share screen.
Okay, Sensei, you must. Okay, now we hear. Sensei, yeah, we can hear Sensei. Ya, bunyinya memang seperti orang bersiul.
Okay. So I'll try this. Okay, please. No?
Like Star Wars.
Coming from, right?
Yeah, the last one is quite new for me.
Oh. Yes. So this kind of wave coming from the generated by the lightning. Very interesting. Okay. Okay, so let's move on to the next. Okay, so by measuring this kind of wave, so we need to detect from where these waves coming. So this is one example so we plot the waveform like this. So if we start this movie, you may see some plot appears like this. So that means like this. So this circle means the intensity of the wave measured by the Arase. So you see that these waves are rotating like this. So that means these waves are coming from this direction. Okay. So by measuring this kind of waveform with a three-dimensional component, then we can determine from where this wave coming. So by using this kind of technique, we determine the source region of the wave. Okay, so this is one example of the wave generated from the lightning. And so when one lightning occurs on the surface of the Earth, then the signal propagates like this along the geomagnetic field line like this. But the propagation speed depends on the frequency. That means higher frequency propagates faster, and lower frequency propagate slower. Then one impulsive lightning discharge occurs. Then we can detect the higher frequency first and the lower frequency the last. Then this kind of spectrum can be measured on board the spacecraft. And this time delay means the propagation length from here to here. So that means the propagation length is shorter. Then this time difference becomes shorter. Okay, so this is this picture. Maybe Umaru-san knows that because he made this kind of spectrum data when he was in our laboratory. So these spectrums are generated and measured by the Arase. So many kinds of spectrums were measured on board the Arase spacecraft. So by choosing this kind of spectrum, we can know from where the lightning occurs and propagate to the observation point. So when the Umaru sensei, Dr. Umaru, is studying the data from the Arase, he developed the automatic detection algorithm of these kinds of lightning visitors from the data measured by the Arase. Okay, so last, I will briefly introduce our space research center named Advanced Research Center for Space Science and Technology. And this space research center was established 2 years ago. And so this center consists of 3 divisions. So one is space satellite development division, and another one is astronomy and astrophysics division, and the last one is solar-terrestrial science division, and I'm a leader of this division. And now we are promoting the new spacecraft named Kanazawa Space CubeSat. So CubeSat means study and training in space science and technology for Kanazawa Cube Satellite. That means, so we call it Kanazawa CubeSat, like this. So our satellite is very small compared with the other spacecraft. the size is 5 centimeters, and the weight is only 50 kilograms. So this is a model of a spacecraft. So the altitude is about 600 kilometers. And this spacecraft will be launched next year. So now we are developing phase. So this is a picture of our Canada CubeSat. Now we are developing. So and in our laboratory, we are developing the onboard software. So this is OBC means onboard computer. And so we are now developing very intelligent onboard software to control this CubeSat. And so we need to launch this spacecraft next year. Then, so we are very busy for the development of the satellite now. Okay, so finally, so we briefly summarize our spacecraft mission like this. So these are the past mission, and these are now in operation. And so now we are developing this Canada satellite here. And now we are aiming a new space mission named Factors. So in this mission, we are planning to multiple spacecraft simultaneously to measure the global environment around the Earth. Okay, so thank you for, so I'll stop here of my lecture. Thank you very much.
Okay, thank you, Kasahara Sensei, for interesting talk. Now I will share the question session for our student. As you may know, Sensei, that we are in computer engineering department in our university. So yeah, I think this is a very new for us. This is a very physics that you already present. So, but I found that you already explained about how to develop intelligent software for your in your satellite. So I think this is also interesting for us, and how we can learn about how to develop the intelligent software. Okay, before I start the question session, the discussion session, I may introduce for our student about what you do in your laboratory in Indonesian. Oke, anak-anak, jadi Pak Kasahara Sensei ini, Profesor Kasahara, studinya ini kan tentang space physics ya, space physics. Tadi Pak Kasahara Sensei menjelaskan juga tentang space weather. Jadi kalau kita mengenal cuaca itu cuaca di permukaan bumi, ada hujan, angin gitu ya. Nah, Pak Kasahara Sensei ini studinya tentang space weather gitu, cuaca yang ada di angkasa. Jadi space itu kita bisa analogikan ruangan di atas bumi, di atas 100 km gitu lah. Jadi di situ ada magnetosfer, ada ionosfer, ada dan sumber aktivitas di space weather atau cuaca antariksa ini adalah matahari. Makanya tadi Pak Kasahara Sensei juga menjelaskan tentang bahwa kegiatan dia itu, penelitian dia itu untuk meneliti tentang aktivitas matahari. Oke, kalau dari anak-anak mau ada pertanyaan, silahkan ke Kasahara Sensei. Ada yang mau bertanya? Boleh di kolom chat ya. Silahkan, Ersan Atiamsah.
Terima kasih atas kesempatannya. And first, let me introduce myself. My name is Ersan Atiamsah. I'm from class TK 4204. I'm sorry, I'm just bad at English. I just want to ask about something. It's about maybe it's some kind of stupid question, but well, I'm just going to ask it. Is my voice Sensei Yoshihara Kasahara Sensei? Can you hear my voice?
Yes.
Yes. Okay. There's a question I just want to ask. How the satellite on outer space is not crash each other, or they have their way, or if they crash each other, is there any kind of handle situation about that?
Oke, coba itu, Ersan.
Atau begini ya. Jadi gimana caranya satelit di luar angkasa bisa nggak tubrukan dan mereka bisa punya jalur sendiri?
Ya, saya kira saya sudah mengerti. Oke,
terus,
dijawab dulu saja ya. Oh, ada pertanyaan lagi, silakan.
Terus kalau misalnya mereka tabrakan, apakah ada penanganan gitu? Kayak seperti itu maksudnya.
Langsung dijawab sama Sensei. Sensei, okay, can you get the question from Ersan? I think he.
No.
Okay.
Yes.
He asked about, how satellite flying in the orbit, and how the satellite can. There is a possibility about the collision or hit about the other satellite. So how we handle this kind of problem?
Okay. So the space environment is quite huge compared with each satellite. So basically, the collision seldom occurs, but actually it could be occurs. So in the case of the large spacecraft, we can control the orbit of each spacecraft, so we can avoid the collision before it occurs. But one problem is that there are so many small objects also orbiting around the Earth, such as so the size is about 10 centimeters or several centimeters. Even though these objects will hit on the spacecraft, maybe the spacecraft will be destroyed. So we call this kind of object as debris, space debris. And this is a very severe problem that if we construct one big spacecraft, for example, so 100 meters times 100 meters squares object, for example. So maybe such kind of small object will be hit on the such kind of object every year. So, for example, NASA is monitoring the such kind of space debris to avoid the collision. Is it okay?
Tadi Ersan gimana dengan jawaban Pak Kasahara? Jadi memang kadang memang tabrakan dengan objek-objek di sana ya, di luar angkasa, kita nyebutnya space debris. Space debris, jadi sampah antariksa kalau di bahasa Indonesia kan. Nah itu memang sebenarnya tidak bisa dielakkan kemungkinan tabrakan dengan space debris itu. Tapi untuk satelit yang besar, kita bisa mengabaikannya. Itu kalau satelit besar ya. Kalau satelit kecil mungkin ya akan parah kalau kena tabrakan dengan space debris. Tapi intinya gini, di luar angkasa sana itu kan sangat luas, sangat besar. Jadi kemungkinan untuk tabrakannya itu pun juga kecil gitu. Oke. Gitu ya Ersan?
Ya.
Kira-kira seperti itulah
Oke.
tangkapan saya ya terhadap dari jawabannya Kasara Sensei.
Ya Pak, saya paham. Saya paham juga kok Pak.
Oh ya, siap. Okay, I think now we move to another question, Sensei. So from Sinta Rodotul. Sinta?
Ya, Pak.
Yeah, you can start your question to Sensei.
Okay, thank you. Hello, sir. My name is Sinta. I would like to ask you something. Maybe I should ask it to China people, but I hope you know it. You know the answer. Okay. I heard that you learn or searching or doing research about sun. Now, I want to ask you, why do China make artificial sun? I don't know why, but I just curious about it.
So I don't know the situation of the artificial sun developed, so studying by China. Yeah.
Oh, okay.
Yeah. Sorry about it.
Okay. Thank you, sir. Sorry.
Yes.
Okay, thank you, Sinta. I think Chinese people want to make artificial sun because they want to study about the fission reaction, nuclear reaction about fusion. Yes, I know. Maybe this is the answer. Okay, we move to another question from Dalvizar Kafilham. Dalvizar, mungkin bisa ditanyakan langsung ini yang ditulis di chat.
Siapa? Sudah terdengar suara saya, Pak?
Terdengar. Silakan.
Okay, good afternoon, Sensei. Let me introduce myself first. My name is Dalvizar Kafila Mestiana, and I'm sorry if my question is out of the box. I just want to ask about the relationship between IT and satellite science. What are the common issues that often occur in IT system that relate to satellites when launching satellites into space? And the second question is for the selection of compressing data, whether the waveform technology can it compress a large data into small ones so that it can reduce the file size, just like WinRAR or something like data compression?
Okay, so can you ask again the first question? First one is
first one is about relation between information technology and satellite science, Sensei.
Okay, relationship.
Yeah, relationship. What are the common issues that often occur in the information technology and in the related to satellites?
Okay, so yes, so actually myself is developing in the information or computer science division, and so so as I showed here the slide, so the we are applying our software scheme on the spacecraft, but the technical part is common for the functions implemented in the smartphone, for example. So that's why. So we are trying to apply these computer techniques into the space mission, and so the why we study the space environment is one is I'm much interested in the space science, and also another one is so as I introduced the introduction part, that the forecast of the space environment is very important, like the nominal weather forecast, because we are going to outside, and we are now developing so many kinds of space structures. In that sense, we need to know, or we need to forecast the environment of the spacecraft. So to forecast such kind of environment, information science is very important, as you know, because such as AI and so on. Okay, is it okay?
Yes, sir, it's clear enough. Thank you very much.
Okay, and the second
The
one,
second question is about the selection of compressing data technique. With
yes,
the waveform technology can compress large data into small ones so that it can reduce the file size.
yes.
So this is about the compressed data technique.
Yes, so this is almost very similar to the one we use, such as MPEG or MP3 and so on. So the very similar technique we use. But in the case of MP3, for example, we can drop the very small sound because we can't sense the small sound when we hear the very large sound simultaneously. But in the space science, all information are very important. And for example, so the JPEG and MP3, we apply the lossy compression. That means we drop some information. But the science or space science, it is very important to keep the information, because we measure the scientific meaningful data. So we can't drop, even though the intensity is very small. So we are studying what kind of, so even though the intensity is very small, we need to keep the important data. So the in such kind of point of view, the technique is a little bit different.
Oke, Dalvizar sudah kejawab.
Sudah, Pak.
Jadi,
Thank you very much,
ya.
Sensei.
Jadi tadi selain metodenya ya hampir sama yang seperti kita lakukan ya kayak di MP3 gitu. Terus satu hal lagi yang dilakukan oleh Sensei adalah dia hanya mengambil meaningful data gitu, Jadi dengan dan membuang data-data yang mungkin tidak diperlukan gitu. Itulah kenapa kapasitas yang dikirim ke bumi nanti menjadi kecil gitu ya, ukurannya menjadi kecil. Okay, we move to another question. Timothy?
Hello?
Yeah.
Okay.
Go ahead.
Okay. Thank you, sir. Hello, Sensei. I want to ask but my question is really out of topic, but I'm really curious. Basically, I'm still in undergraduate program, and I'm really curious how to prepare ourselves if we want to take master degree in Japan on engineering field, specifically maybe computer engineering. And as a foreigner, yeah, we should to take a Japanese course, but can we take the Japanese course in our country, or we should take the Japanese course in Japan? And then for the foreigner, what language will we use in the class? Will it use Japanese or English? And how to get any scholarship? Thank you.
Okay. So, so you are asking the environment in our university. Okay. So, for example, so now our Canada University is inviting so many foreign students And especially for the master's course and the doctor's course, we teach the many subjects in English. And so you can come, even though you don't know well about Japanese. And now we are developing such trial to the bachelor students. So some of the subjects are provided by English. So we welcome a lot of foreign students in our university. Okay.
Okay, thank you,
Thank you, Moti.
Sensei. Siap, Pak.
Okay. There is another question from student. Okay, go ahead. Yeah, I think Sheikh Rifan mau tanya, silahkan.
Okay, hello, good afternoon, Sensei Kasahara. I would like to ask you a question. Is there any relation between unusual solar activity with our space weather? Like, for example, the unusual activity of our sun affects our radio activity in Earth. Like, we are not allowed to use our phone because the electromagnetic power of the sun. Maybe that's it. The question. Did you get
Sensei,
my
can you
question?
get the question?
You mean the yes, so you are mentioning about the space weather and so the sun activity affects
Yeah.
our life. Okay. Yes.
Yes.
Yeah. That's it. That's it.
Yeah. So the effect is so many kinds of. Yes. So yeah. So for example, so in space we have radiation hazards, and also solar panels will be degraded. And for example, on the surface of the Earth, one very important, so famous case is stopping of the power supply in Canada because of the magnetic storm. Yeah.
Oke, Yofi tadi udah kejawab?
Yeah, I think so. Thank you, sir.
Okay, is there any question from students? Okay, Raja Ilham, go ahead.
Suara saya kedengaran nggak, Pak?
Terdengar. Silakan.
Hello, Mr. Yoshia. Nice to meet you. My name is Raja Ilham. So I want to ask you about something. Lately, I've been read about news about the Russian old rocket debris that broke down on 8 May, and it falls into the earth, into the Indian Ocean. So I want to ask you about how Japan Space Agency handle if the rocket debris of Japan spaceship are broke down into the earth, and how can you calculate it where it fall, and are those things bring radiation and those things bring out radiation to so it can change the climate change in the earth. Thank you.
Okay, so you are asking the drop of the spacecraft and the rocket. Okay.
Yes.
Okay, so in the case of Japan, fortunately, we are facing the Pacific Ocean in the east of Japan. So we launch our rocket toward the eastern direction. That means the rocket will be dropped on the in the Pacific Ocean. And as for the spacecraft, so very small spacecraft will be burned out before dropping on the surface. But the large size of spacecraft will be dropped without burnout. So, so the in our case, we we need to design the orbit when we stop our space mission. We change the orbit to drop the spacecraft as soon as possible. But in the other countries' case, as you know, that they don't care about it. So that means we can't know when and where it will be dropped. Yeah, that's a problem.
Oke, Raja Ilham, sudah kejawab?
Okay, thank you, Mr. Yoshia.
Okay, any question? Any more? Okay, Sensei, let me ask about the, so you also upgrade or change the software in your satellite. So how you change the, or how you upgrade the software?
Okay. Okay. So we have another set of CPU and so on. Okay. So here is a picture. So these both are almost the same. Same as the onboard receiver. So we and develop our software and install the software on this breadboard, so we can test the software using. And then, so after the test, so we send this software into the spacecraft.
I see. Okay, yes. Okay. And one more, so you, in your data compression, so you all only retrieve or only take the meaningful data. So it means, so you study about previous data to get the meaningful data?
Okay, so very important question. So yeah, we basically, yes, so we learn about the past data, and we know which is meaningful. And but there is one problem, because we know, so if we get and learn about the characteristics of the data, we don't need to get anymore, because for example, so for the planetary mission, we need to get very new and rare data. That means we can't learn about it. So we need to discover the new one. So in that sense, we learn about the well-known data, and then we pick up the data which are not well-known for the downlink to the ground.
Okay, and then one more. Is it possible to hear the sounds like cars, whistler by our ear, or we
Okay.
must convert?
Okay, so to hear the wave, we need to convert to the sound. So on the spacecraft, we cannot hear. So after download this waveform signal, we convert the wave to the sound, and so that we can hear the signal.
So even in the polar region, we cannot hear the waves.
Yeah.
But actually, I heard from my sensei, maybe the aurora also has sounds. So is it real?
Yes. Yes.
Is it
right.
the same with the chorus?
So the sound is different because okay. So as you show the shape of the spectrum like this. So this is a shape of the sound. So that's why we can hear that kind of sound. And oh, sorry. In the case of right whistler, so it is going down from high to low. So that's why we can hear. So the shape of the wave generated from the aurora is different. So the sound is different.
Okay, thank you. Okay, any more question from the students?
Mas Praitno.
Yep. Oh, okay. Umar Sang already.
Okay.
He came back.
I'm sorry, Kasahara Sensei.
Yes.
I need, yeah, I need to move to different location in order to get the signal, Sensei. So unfortunately, side of Indonesia. I'm in the remote island, so the signal is not very good in here. So I'm sorry for the inconvenience. Yeah. So I think it is near the end of the session, Pak Praitno. So it's already 15:27. So we already today. So once again, thank you very much for Kasahara Sensei to prepare the presentation today. And also on behalf of Telkom University, we are really appreciate for your presentation today, and hopefully we can have a collaboration in the future. Basically, I really want to discuss with you in other discussions, because we want to have a cooperation between Kanazawa University and also Telkom University for student exchange, research collaboration, and also for the continuing study for our student to master degree, and also our lecture for doctoral degree, Sensei.
Yes. Okay. Yes.
Okay.
Yeah, we are welcome. Yes.
Thank you very much.
Yes.
Thank you very much, Sensei. Maybe for this session, maybe you have some closing remark to share with our student before we close the Zoom session for today. Please, Sensei.
Thank you. Yes.
Okay. So, Pak Praitno,
yep.
Maybe we can close for today's discussion.
Okay. Okay.
Okay. Once again, on behalf of Telkom University, thank you very much for Kasahara Sensei.
Yeah. Thank you.
For Mr. Praitno, and also for all of my students in Telkom University, and also for the guest participant, yeah, like Mr. Bayupati, Ibu Desi, Pak Ardian, and Pak Jay, yeah, which is the Kasahara Sensei student for the past. Thank you very much, Sensei. Goodbye and good afternoon. Keep healthy, and hopefully we can meet in another time. Yeah. Thank you.
Yes.
Bye bye, Sensei.
Bye bye.
Thank you very much.
Thank you very much. Okay.